Hello friends, today I will discuss with you the time temperature transformation diagram of Eutectoid steel that according to the iron cementite phase diagram gives 100% paralytic microstructure upon equilibrium cooling. And then we will discuss what actually happened during the incubation period, and then we will see how the rate of nucleation and the rate of diffusion of carbon atoms play their role simultaneously in changing the overall transformation rate that eventually affects the overall incubation period and changes with temperature. So friends, watch this video until the end. This is part 2 of lecture 2, the time temperature transformation diagram. Previously we have seen that how the series of isothermal transformation curves of eutectoid steel drawn at different temperatures extended into the time temperature transformation diagram. So friends, let's start our discussion from the time temperature transformation diagram of eutectoid steel. The iron cementite phase diagram has told us that if we slowly cool down the eutectoid steel, we will get 100% paralytic microstructure. But the results of time temperature transformation diagram has revealed us that we may also get magnetic structure or martensitic structure or even retained austenite. That's all depend upon the cooling cycle. At a lower critical temperature, which is 723 degrees centigrade, the Gibbs free energy of austenite is equal to the Gibbs free energy of pearlite. Therefore, the austenite to pearlite transformation will complete in infinite time at this temperature. In other words, the austenite to pearlite transformation rate will be 0 for all practical purposes at this temperature. Therefore, it is essential to undercool the austenite below the lower critical temperature for the transformation to start. Below the lower critical temperature, the free energy of pearlite is actually lower than the free energy of austenite. So, pearlite is thermodynamically stable, and the lower the free energy of pearlite, the more is the stability of the pearlite. If we cool it down to temperature T1, then the driving force would be less than compared to cooling it to temperature T2. You can see here, as we have increased the undercooling, the incubation period is decreasing, but only up to a certain temperature. After that, it goes on increasing. You may ask, sir, why is that so? In a minute, I will explain it. If we plot the rate of transformation with respect to temperature, then we can see that an increased degree of undercooling initially increases the transformation rate by providing a greater difference in free energies of austenite and pearlite or austenite and bainite. The question why the incubation period is longer at low temperatures can only be explained if we know what actually happened during the incubation period. Actually, during the incubation period, the atoms come together to form nuclei for transformation to start. So, the transformation does not start until the nuclei of a particular radius are formed. As the transformation of austenite to pearlite or bainite proceeds by the redistribution of carbon atoms, so these transformations are the diffusion control transformations, and the rate of diffusion of carbon atoms decreases exponentially with the decrease in temperature. If the temperature is too low, the atoms will move so slow that even the formation of nuclei will become very difficult because the atomic moments are very sluggish. That is why longer incubation period has been observed at lower temperatures. This means that undercooling affects the rate of transformation in two ways. On the one hand, an increased degree of undercooling increases the transformation rate by providing a greater difference in free energies of austenite and pearlite or austenite and bainite. On the other hand, an increased degree of undercooling reduces the transformation rate by lowering the rate of carbon diffusion. So the overall transformation rate will be like this, which is clearly explaining that why we have observed the C curve for the beginning or end of transformation. Because where there is a high transformation rate, there is a shorter incubation period. Both the rate of nucleation and the rate of growth are zero at eutectoid temperature, and they also tend to be zero below 200 degrees centigrade. So, cooling below the 200 degrees centigrade will result in a diffusionless product, which is called martensite.